And here we are at ptable.com. ptable.com. I just want to show you a little bit about how the electron configurations in atoms fits in with the periodic table. Alright, now let's go to the main page here, and we can see you're all familiar with the basic structure, the periodic table here. There's 2 columns over here, there's 10 columns in the middle, there's 6 columns over this side. There's 3 rows that rise up above the main body of the table. And by the way, this is a fantastic website. It's packed full of all sorts of information. You can click on any of these elements to get more information. You can click on properties up here, and you can see things like ionization energy, which we'll be looking at, electronegativity. You can look at the density, and it shows you, it's got them shaded according to density, and you can really get a good feeling for the trends in the periodic table, which we'll be looking at soon. But today I want to focus on the electron structure, or we could say the energy level structure of atoms. And you'll notice that one of the things that happens when you click on this orbitals tab is that the helium flips over to the left hand side, whereas on the normal table it's over on the right. And this is to show you that the table is structured according to the way the electrons are arranged around the atoms. Now, first of all, let's take it at its most basic level. If I look here in the center, I see these little blue boxes here, and I see these symbols: 1s, 2s, 3s, 4s, 5s, 6s, 7s, and then 2p, 3p, and so on, and 3d, 4d, 5d, 4f, 5f. Okay, and they have these funny little shapes that show up on the sides here. Those shapes are called orbitals. Okay, and orbitals are really, you can think of them as subdivisions of what are called sublevels, which are the S, the P, and the D, and the F. And then the sublevels are subdivisions of what are called the energy levels: 1, 2, 3, 4, 5, 6, 7. Now, energy levels are basically those rings that you see around the atom in the Bohr model. So if you look right here, you can see a picture of the rings. So I'm going to click on this one, and you can see kind of shell structure, the concentric rings. As I move up here, you can see that there's more and more concentric rings. So this is the 1, 2, 3, 4, 5, 6, 7. The integers here represent what we call the principal energy level. Now these are the rings that we draw around the atom in the Bohr model. They have to do with distance from the nucleus. So if an electron is in a higher principal energy level, say level 3 versus level 2, if it's in a higher principal energy level, then that electron has a higher energy, and it is on average further from the nucleus than if it's in, say, level 2. So an electron in level 3 is further from the nucleus on average than an electron in level 2. Now let's see what happens as we move across the table. So right now I'm in hydrogen. You'll notice there's a little arrow in this box that says 1s, and that little arrow represents an electron. Right now there's an electron in the first energy level. If I move to helium, I'll see now that there are now 2 electrons in that first energy level. And if I move to lithium, I'll see that there's 1 electron in the second energy level. Now, something we can notice right away is that we are now in the second row of the periodic table, and we have an electron in the second energy level of the atom. As I keep moving across, go to beryllium, for example, I can see I'm still in row 2, and I still have electron in the second energy level. In fact, that's the outermost occupied energy level. And notice now that I have 2 in that. Now let's count all these arrows up. 1, 2, 3, 4. That's 4 total electrons. And my atomic number of beryllium is 4. Now the atomic number is the number of protons, but in a neutral atom it's also the number of electrons. Let's move across to boron. I click on boron, and I now see an arrow pops up right here next to 2p. Now the 2 next to the p means that I'm still in the second energy level. I'm still in that second shell around the atom. The P means that I'm in a second subdivision. I'm in a different subdivision of that shell. It's called the P subdivision. And you can see that the orbital has changed shape. So when I'm in an S sublevel, my orbital is round, it's a sphere. When I'm in a P sublevel, the orbital is more like a dumbbell, and it can change its orientation, so it can be on different kind of axes. It's pointing out at you, or it's up and down. But in terms of energy level, I'm still in the same energy level. So that's the second energy level, and I'm still there. And when I click on carbon, now I'm still in the second energy level. Notice another arrow popped up right here in the second box next to the 2p. I now have 1, 2, 3, 4 electrons in the second energy level. I click on nitrogen. Now I have 1, 2, 3 arrows, 3 electrons in the 2p, and still have 2 in the S, in the 2s. So in energy level 2, now energy level 2 is represented by all the 2's, the 2s and the 2p. So I have 1, 2, 3, 4, 5. It's 5 electrons in the second energy level. Oxygen has 6 electrons in the second energy level. 1, 2, 3, 4, 5, 6. Fluorine has 7. 1, 2, 3, 4, 5, 6, 7. And neon has 8. 1, 2, 3, 4, 5, 6, 7, 8. When I add one more electron, so if I go from neon and go to sodium, I now have 11 total electrons. 2 are in the first shell, the first principal energy level. 8 are in the second shell. 2 in the S subdivision and 6 in the P subdivision. Okay? And then 1 is now in the third principal energy level, the third shell. I'm in row 3 of the periodic table. So I'm in row 3 of the periodic table, and I have 1 electron now in the third shell because I'm at sodium. If I go to the second group of the periodic table, magnesium, I now have 2 electrons in the third energy level. If I go to group 13, aluminum, I now have 2 electrons in the S subdivision of the third energy level, and 1 electron in the P subdivision of the third energy level, for a total of 1, 2, 3 electrons in the third energy level. In other words, 3 electrons, or I'm 3 atoms over in the third row. I'm 3 atoms over in the third row, so I have 3 electrons in the third principal energy level. I'm 4 atoms over in the third row with silicon, so I have 1, 2, 3, 4 electrons in the third energy level, the 3s and the 3p. Remember, the 3s and the 3p are in the same energy level. They're in the same shell. For phosphorus, I now have 1, 2, 3, 4, 5 electrons in the third energy level, and I'm 1, 2, 3, 4, 5 atoms over, 5 elements over in the third row of the periodic table. When I'm 6 elements over in the third row of the periodic table with sulfur, I have 1, 2, 3, 4, 5, 6 electrons in the third shell. When I'm 7 electrons over, group 17, then I have 1, 2, 3, 4, 5, 6, 7 electrons in the third shell. And when I'm 8 electrons over in argon, I now have 8 electrons in the third shell. Now, one of the things you'll notice is with the noble gases, when I go from neon to argon to krypton, and I could go all the way down, but notice, let's just look at neon and argon. Neon has 8 electrons in the second shell. Argon has 8 electrons in the third shell. Now we'll notice that if we go to krypton, we have 8 electrons in the fourth shell. We also have some electrons in the D sublevel of the third shell, but the fourth shell is the one that's furthest out, and that has 8 electrons, just like argon had 8 electrons in its outermost shell, and neon had 8 electrons in its outermost shell. And it turns out that as we go down the table, krypton, xenon, radon, they will all have 8 electrons in their outermost shell. Radon's outermost shell is 6, and it has 1, 2, 3, 4, 5, 6, 7, 8 electrons in its outermost shell. The only exception to that rule is helium, and that's because helium only has 2 electrons, and its outermost shell is shell 1, and it can only hold 2. So it still has a full outermost shell. Okay, now one of the tricks I want to show you is to figure out how many electrons are in the outermost shell. Now again, the outermost shell, we're looking at these numbers here, 1, 2, 3, 4, 5, 6, 7. We're looking for the highest number that the electron occupies, and we're looking for how many electrons, or that the atom occupies, and we're looking for how many electrons are in that shell. There's a trick for that, for figuring that out. Just look at these numbers up here above the periodic table, 1, 2, and then let's jump over here, 13, 14, 15, 16, 17, 18. When we're in either the first two columns or the last six, then the number of electrons in our outer shell is 1 if we're in the first column, 2 if we're in the second column. Let's just check that to make sure. Magnesium is in column 2, group 2, and it has 2 electrons in the third shell, which is its outermost shell. So the number of electrons in the outer shell is equal to this number up here. Now when we jump over here, the number of electrons in the outer shell for group 13 is not equal to 13, but it is equal to 3. Look at boron. Boron, outermost shell is 2, 1, 2, 3. 3 electrons in the outermost shell. Carbon, outermost shell is 2, 1, 2, 3, 4 electrons in the outermost shell, and look at that, number 4 right there. Now again, it's not 14, it's 4 electrons in the outer shell. So when we're over here in what we call the P block, because we're filling the P sublevel, we can see that it is the second digit in the group number that refers to the number of electrons in the outermost shell. Those are also called the valence electrons, or the valence shell, the electrons in the valence shell. So we have 3 electrons, 4 valence electrons, 5 valence electrons, 6, 7, and 8. Again, neon has 8 electrons in its outermost shell. 1, 2 in the 2s, 3, 4, 5, 6, 7, 8. Shell 2 has a total of 8, group 18. So 8, 7, 6, 5, 4, 3, 2, 1. Now when we're making Lewis structures, which we'll be doing in the future, that's what we're going to be using to just quickly figure out how many electrons are in the outermost shell, because it's those electrons that are in the outermost shell which are going to make the biggest difference in the behavior of that atom in terms of its bonding behavior, if it's making ions or if it's making covalent bonds. Alright, and that's enough for now.